Hello, this is part 3 of our lecture in RREF, Reduced Row Echelon Form. So what this theorem is telling us is that a matrix, basically any matrix, can be transformed by applying these operations, applying operations of swapping rows, multiplying by scalar, and then multiplying by scalar and adding to another row and replacing a row. By applying those operations, it's possible to transform the original matrix into another matrix that is in reduced row echelon form. So um, in this matrix, this new matrix considered the RREF of the original is a matrix that is row equivalent to the original because it's obtained by this type of operation. So that's precisely what we would like to exploit or make use. And so existence and uniqueness, this this is the first theorem establishes the matrix can be transformed or changed into an RREF form, and the second theorem is saying, well, um, basically that RREF is unique for it exists and is unique. Okay, so it's just technicality. So let's go and review how this applies to this type of problems. This is what we're interested in. So here we have a system of equations. It has three variables, three equations. We form the augmented matrix. This augmented matrix is a matrix that is 3 by 4, right? So this sub submatrix or subset here is 3 by 3, and that precisely corresponds to the coefficient matrix of coefficients of this original system. But we formed augmented matrix, 3 rows, 4 columns, and now we work our way row by row. So let's see what happens to the first row. We swap row 1 and 3, okay, and that is already giving us the advantage of we get a 1 on position row 1 column 1 of this augmented matrix, so that's good. And then what comes next is multiply row 1 by -5 and add that to row 2. So you can see here that by multiplying row 1 by -5 we have -5, 0, -20, -25, and adding that adding this new row to row 2 is going to create a 0 on that first entry of that row. So -5 plus 5 is a 0. So we multiply row 1 by -5, add that to row 2, and substitute, replace row number 2, and that gives this new matrix. And so what we do next is multiply row 1 by 7, add that to the third row, add that to this row over here, and then we can see right away that there are zeros being created and on some of these entries of this matrix. And now we work with row number 2. We multiply the second row by 1/5, and that's because here we had a non-zero entry, which is 5, and we multiply row number 2 by 1/5, and that gives us a number 1 on that position. And so let's see what we do next. Multiply row 2 by 6 and add that to row 3, and that has the advantage of creating some it's giving us some 0 entries here. So it's giving us this 0, which will be important, but let's see if there is anything else to do here. So what happens to row 3? Finally, in row 3, we're going to multiply row 3 by the number 5 halves, or 5 divided by 2, and that gives us a number 1. That gives us a number 1 in this position, and with a 1 there, we can then create zeros on following positions. We multiply row 3 by 13 divided by 5, add that to row 2, replace row 2, and then multiply row 3 by -4, add that to row 1, replace row 1. So at this stage, there is nothing else to do. So this is now, this matrix here is a matrix in RREF form. You should go and check all those conditions. Each rows of zeros located at the bottom. There is no rows of zeros. For each non-zero row, the first leftmost non-zero entry is a 1. And then for each of those ones, there are zeros above and zeros above and below that one. So those are indeed um, pivot or leading ones, and then these columns are pivot columns. But once this is expressed in this form, then coming up with solutions is actually straightforward. And then we'll see that this is telling us that x3 equals to, okay, so this here corresponds to a system of equations. If I read, I'm gonna have to write this backwards here, but I'm gonna read the last equation first. So the last equation says 0x1 plus 0x2 plus 1x3, and that equals 2. Okay, that's what I see. That's what we see from the last equation. The second equation says 0x1 plus 1x2 plus 0x3, and that is equals 5, is equal to 5. And then the first equation says 1x1 plus 0x2 plus 0x3 equals minus 3. So these three equations will say x3 equals 2, x2 equals 5, and x1 equals minus 3. Okay, and those values are values of x. X1 equals minus 3, x2 equals 5, x3 equals 2. Those values are in fact solutions of the system associated with this matrix, but because of some of those theorems, we know that those are solutions of the original system, the system from where we first formed the augmented matrix before we started applying these row operations. So in this case, we are going to say that we're going to write a set containing these values listed here as a vector, the values of x1, x2, and x3, minus 3, 5, and 2, minus 3, 5, and 2, listed here as a column vector, and then we enclose that as a set, and we say this set contains this vector, and in fact, this is one of those cases in which the system has only one solution. This is the only solution to the original system, and the solution set contains, in this case, only one element.